Not so long ago, I was asked the question, okay, so we've been going about this and we've seen that we have vertical asymptotes and we have horizontal asymptotes, but hyperbolae have not necessarily horizontal nor vertical, but some sort of line that they tend to approach. And so they were looking for, well, how does this kind of tie into that? How can I see a hyperbola without deriving the standard equation for it? And so I thought about it a little bit. You know, that's a tough question. And so then I did a little bit of research, and we talked about it a little more as a class. And we found in the book where it mentioned it, but it still doesn't make sense until I started thinking about the limit. Okay, so let's go ahead and let's take a look at what happens if you perhaps have a slant. And the condition that you have to test is that the degree of the numerator Ator is exactly 1 larger than that of the denominator. Okay, so let's just take a gander at something that might have this. So I'm going to consider something like the following. If I have f of x, and that's equal to x squared plus 1 all over x, then the thing to do here is going to be to A factor as best I can, and then B split it up. Okay, and so I'm going to try to rework this whole function as a sum of functions rather than as the difference of functions here. And to do that, I'm simply going to break up the fraction. Okay, I'll take a look at a more complex one a little later, but I'm going to go ahead and break up the fractions so that if I look at it, that's really x plus, and then I have 1 over x. Okay, now let's look at the behavior at the limit. Okay, so as the limit as x approaches infinity. Okay, so now the terms are what we consider. So here's one term, here's another term. And so what happens to each term? Well, as x goes to infinity, 1 over x gets very, very, very small, and so that tends to 0. However, the limit as x tends to infinity of x is infinity. And so we have a distinct problem here. One of them is driving off towards infinity, one of them is just going away. And so now consider for a moment what it is you're comparing. And we're saying, what is the limit as x tends to infinity? Okay, that is what it's tending to. And so if we look at, if we start breaking the limit down and what it's trying to say, this number here is what y is tending to. It's trying to tend to 0 and to infinity at the same time. But really, it's looking at the sum of them. And so if I look at just the y and how the y behaves, then this first part, or the second part here, is just going to go away, and y is going to look more and more like x. Y is going to tend to infinity, but it's going to look more and more like x, which means that this has an oblique or a slant asymptote at y equals x. And so it's going to start looking like y equals x. Okay, now this only happens when you have exactly 1 because it's linear. Now, the problem that we have later on is that if you have it 2 or 3 or 4, well, now you have a problem where you have x squared here, and now it starts looking a lot funkier. Okay, so it tends off to infinity and it may be asymptotic, but it's not something that we're considering at this particular moment in time. But this is a way to break down and to really examine what the limit is looking at, because the limit is considering the behavior of the whole function, which is y, when x tends off to infinity. And so as you look, then the separation between these two values gets smaller and smaller and smaller and smaller, and in fact tends to 0. And so y starts looking more and more like x as it tends off. Okay, so now the question is, of course, now continue this on, what would it look like? Okay. All right, so now we've got that thing. When it goes off to infinity, it starts looking like y equals x. So the limit as x tends to infinity of f of x is x. Okay, the limit as x tends to negative infinity of f of x is negative x, or is still x, really. Okay, because it's still going to be negative infinity, which is what x is. All right, so now it's just tending to y equals x. So that's what the infinite is doing. So if we go up to our list here, we say, what are any restrictions on the domain? Well, x can't be 0. We've determined our behavior at infinity, determined any places of indeterminate behavior. When the bottom is 0, the top is not, and so we're done. And so the domain of f is limited. It's all real numbers, not x equals 0. Or I should say, let me put it in a little different way. X such that x is not equal to 0. So that's set notation for that. Okay, so now the next thing we do is take our first derivative and determine points of relative extrema, or critical points, and then we can use the first derivative test to gather whether it's increasing or decreasing. Okay, so now f prime of x, take the derivative of the top, which is 2x, times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. And so if we clean this up a little bit, we have 2x squared minus x squared is x squared. Then we have minus 1 all over x squared. Okay, so now where is that 0? Where is this 0? We have a 0 at x equals plus or minus 1. And now how do we test that? Well, you can do it one of two ways. You can either test to see if it's increasing and decreasing on either side with the first derivative test, or you can just simply take the second derivative and check for concavity at those points. And so the second derivative is equal to the derivative of the top, which is 2x, times the bottom, which is x squared, minus the derivative of the bottom times the top, all over the bottom squared. Okay, so now we have 2x cubed minus 2x cubed, and well, that's gone. And so all that's left is a 2x over x to the 4th. All right, so now, see if this makes sense. We can take the derivative. Hang on, I don't like this derivative, so I'm going to check it really quick. The derivative of the top times the bottom minus the derivative of the bottom times the top, okay, all over the bottom squared. So 2x cubed minus 2x cubed, yeah, okay, minus 2x minus 1, okay, so I like it now. All right, so now let's check them at plus and minus 1. All right, well, we can just take a look at this and say, okay, no matter what, the bottom is going to be positive. It will. So we have now, all we have to do is check the signs. So when we're looking at negative 1, we get something that's less than 0. When we're looking at positive 1, f double prime of 1, we get something that's greater than 0. So that means that we're concave down here, we're concave up there. So this is concave down means we have a maximum. So we have a max. these two things right along with this, this implies that x equals -1 is a maximum, is a relative max, and x equals 1 is a relative min. So now if we go up to the top, or if we go back up to the original equation, can we find any zeros? No, no zeros. So it doesn't cross, it doesn't look like it crosses the x-axis. Okay, because I can't get that to equal 0 at all. It just doesn't. So it doesn't cross the x-axis. So now, as it tends to infinity, though, it looks like y equals x. And so I've got, draw my, okay. And now it's going to tend towards this magical line of y equals x. This is y equals x. And now I have to find all those points. All right, so I'm going to bring down my original equation again. This is x squared plus 1 all over x. And so f of -1 is equal to 2 over -1, which is -2. So I have the point -1, -2. And then I have f of 1 is equal to wow, just complete brain fart here. I have 2 over 1, which is equal to 2, and so I have 1 comma 2. And now I said, oh, it doesn't cross the x-axis because it can't make the top 0. Well, we have a problem at 0 because we have a vertical asymptote. And so since we have it bottoms out at 1 comma 2, if I drag this up and here's 1, then here, and now I have a vertical asymptote at 0. And so it's going to bottom out and then it's going to tend towards this. So it's going to look a lot like that. And then on the bottom side, it's at -1, -2 that it tops out, but at 0 it goes to -infinity. And so it starts going, and so you notice it never does cross. And we didn't need to use every single one of those 10 things there either. All right, so this is what it's going to look like. It's not bad. It's not really. And so we just got this from the first derivative, but more importantly, we got this by looking at its behavior at infinity and splitting up that fraction. That's the key in this one. We had to split this fraction up to look at what does each term do at infinity, because one of them goes away, the other one dominates. That's the key to this curve sketching and using limits at infinity.